All right, you guys, here's solutions video take 2. I was so disappointed yesterday. It was such a great video, but it just didn't work out, but that's okay. All right, so to keep this brief, solutions are usually measured with a unit called molarity. There are other units that are used. However, first of all, the AP test does not assess those other units, but just so you know, when you go to college chemistry, you will probably be taught about a unit called molality or parts per million or parts per billion. There are different ways to measure, okay? But molarity is hands down the one that chemists use the most, okay? And when like I order solutions from chemical supply companies, they are typically sold in molarity quantities, you know, so if I need to order hydrochloric acid, I can choose like 1 molar HCl, 2 molar HCl. So even though there are other units available, like really for practical purposes, molarity is the one chemists use the most, okay? Which is why it's the one that they look at on the AP exam. All right, so, and part of the reason that molarity is the most frequently used unit is because of the way the solutions are made and the amount of solute compared to the amount of solvent, okay? So molarity very simply is defined as moles of solute divided by liters of solution, okay? A couple things about that. As you know, but we'll just review, all right, there are 2 parts to every solution. There's the solute and the solvent. The solute is the substance that's being dissolved. Typically, it is the substance that is present in a significantly smaller quantity. The solvent is the substance doing the dissolving. A lot of times it's water, okay? Water is known as the universal solvent. And for any solution that has polar solutes or ionic solutes, water is going to be, first of all, the cheapest, and secondly, one of the most effective solvents for getting those particles distributed. The only time we really use solvents that are not that's not water is when we have a nonpolar solute, because as you can imagine, nonpolar solutes don't mix with water. They're immiscible, right? Because water isn't motivated to socialize with nonpolar substances. So if you have a nonpolar solute, then you're going to need a nonpolar solvent, okay? But really, in our daily world where water is like such an abundant substance on our planet, most substances dissolve in water, and most solutions that we use in the lab are water-based solutions, okay? So a couple of things about this. If you're gonna make a solution, so I'm gonna like show you the definition and we're gonna go through a problem, but I'm also gonna show you how you can use this information and then make a solution. So first things first. We have moles of solute, okay? But as you know, you guys, moles of solute, like you can't measure moles in the lab very easily. There's no piece of equipment called like a molometer or something like that. There's no piece of equipment, there's no device that'll measure moles directly. Instead, we can measure grams, and through molar mass, grams and moles are connected, okay? So our solute is typically measured in grams, okay? Because that's just the most practical. And converted to moles using molar mass. All right, so when you need to measure your solvent or solute, I'm sorry, you're going to use an electronic balance. Okay, solvent. Now, this is where it gets interesting. Your solvent is typically a liquid, so that can be measured in liters, or, you know, depending on the size of the solution, like maybe even milliliters, but you can numerically convert that to liters. You know, most of us use graduated cylinders or volumetric flasks, which I'm going to show you in a second. All of these devices typically measure in milliliters, okay? And the solvent, because it's a liquid, is usually pretty easy to just pour, and then you get the exact amount you need. Because the solute particles are such a very, very small portion of the volume of the solution, usually the volume of solvent is pretty much the same as the liters of solution, okay? Because for the most part, it's your solvent that's contributing the volume, not your solute. And I would say, like, if you think of the ocean, when we look at it, we're like, wow, look at all that water. Nobody's sitting there going like, wow, look at all those NaCl ions, right? Because even in, like, if you were to go get like a pail full of water, like, you know, most of what's in that pail is actually water molecules. Very little of what's in that pail is actual sodium chloride ions in terms of volume, okay? So the volume of our solution is usually the volume of our solvent, you know, we're pretty darn close. So, all right, so I'm going to show you how you would actually do this in a lab. We're going to do a little bit of math first, and then I'm going to make this solution for you. So let's say you had a problem, because here's the thing. You need to understand this like mathematically and how to do the calculations. But this is a concept, and they ask this very often, like, how would you prepare a solution using this? Okay, this comes up on the AP exam. Not only do you need to understand the math, but you need to be able to put the math into a laboratory context and explain how do you know what to do based on that, okay? So the question is, and then I'm gonna do it, how would I make 200 milliliters of a 0.15 molar NaCl solution? So I have salt. If you're wondering why I'm not wearing goggles, it's because it's just salt water, okay? You always begin with the concentration of your solution in mind. Like, you usually know what concentration you want, okay? So what's gonna happen here is I wanna make a 0.15 molar NaCl solution, okay? And that is equal to moles of solute, right? Divided by liters of solution. And I'm gonna just go slow here and walk you through this. You can abbreviate solution SOL''N. Okay. So let's think about this. If we are making an NaCl solution, our solute is going to be Na, right? Okay, or NaCl, sorry. Our solute's gonna be NaCl. We don't know how many moles we need right now, okay? So we're gonna say 0.15 molar NaCl solution equals moles of NaCl, we don't really know anymore, divided by liters of solution. Do we know anything about that? Read the problem again, okay? What do we know? We do know that we need a 200 milliliter solution. And you can easily convert 200 milliliters to liters. So 0.200 liters of solution. Now, if I bring out my calculator, okay, give me a second. I'm gonna go side by side here so you can see it all. Try to ignore the stuff you see down there. So now, to find my moles of NaCl, I'm gonna do 0.15 molar times 0.200, right, equals moles of NaCl. And so what I'm gonna get there is 0.03. And I can actually have two sig digs. So I'm going to add a 0 on there. All right, moles of NaCl. So that's how much solute I need. But again, you guys, I don't have anything to measure that, do I? Okay, I don't have a mole meter. So knowing that I need 0.030 moles of NaCl, I mean, that's nice, but like I can't measure that. So what I actually need to do is convert to grams, okay? So I know that for every 1 mole of NaCl, NaCl has a molar mass of 58.44 grams, okay? So then if I multiply, give me a second, split screen again, okay? So if I multiply that, I still have my 0.03 on my thing, times 58.44, I get 1.75, which again, sig dig wise would round to about 1.8 grams of salt, okay? So, which I'm gonna squeeze in right here, 1.8 grams of NaCl, all right? So practically speaking, that is what I need, okay? And so now what I'm gonna do is I'm gonna show you how you would use all that information. And I'm gonna try to like tilt the camera so that you can see the equipment and not me, which I think makes it kind of awkward, but it's fine. So what we're gonna do here is I'm gonna put some NaCl in a container just to make it a little bit easier for me to get out. I might need a little bit more than that. I chose to use a yellow sheet of paper because with the salt being white and this being a video, I thought it would be easier for you to see the salt crystals on the scale if I put them on a yellow sheet of paper. Okay, I am going to show you, like right now, my scale has some mass on it from the paper. I'm going to hit 0 because you always want to zero that out. Now, my scale that I'm using goes to the thousandths decimal place. And remember, for sig digs, we only need 1.8 grams. So, like, honestly, I'm sitting right below a vent, which is why, and I'm like sitting here breathing on the scale and I'm pushing my elbow on it. That's why the thousandths place is moving so much, but it doesn't matter because we basically need 1.8. So we're only going to the tenths. So really we're going to be okay. Initially, I can put a decent amount on there just to get the process started. You always want to get a sense of like what size sample is going to create like what size pile. So you don't want to go like too crazy, but like right now I'm at about 1.55 grams. So I'm going to slow down a little bit just so I don't go over. Okay. I'm getting close to 1.7. I'm at 1.699. In yesterday's video, of course, I got to exactly 1.800. I assume that'll be impossible to replicate today. Okay. I'm at 1.75 approximately, 1.76, 1.773. Oh, look at that. Oh, wait. I went back down. Oh, now I'm a little over. I'm going to take a tiny bit off. One more green. Okay, I'm at 1.807. I am going to try to be pretty exact here. But it's hard to do. All right. 1.805. 1.8 0.02. That's probably as close as I'm going to get. All right, so here is my salt, okay? You can see this. And remember, we're going to make 200 milliliters of solution, and we're going to use something called the volumetric flask, which I'm going to do a close-up of so that you can see it. This is a very specific flask that has been designed to measure exactly 200 milliliters. When chemists make solutions, these are the flasks that they want to use because you can tell exactly where you need to measure to. See that little white etched line up by my thumb? Okay, I'm trying to like rub my thumb behind it so you can see it's like right there on the front. If you, and you'll notice, so like you have this huge bulb at the bottom and then this very narrow neck where that line is, because that line is exactly where your meniscus needs to land to make this perfectly 200 milliliters. So these are super great devices for precise measurements, which anytime you make a solution, you want a precise measurement because, you know, depending on what you're using it for, that's going to affect the amount of product and stuff you make, and you want to make the right amount. So a couple of things I'm going to show you here. First of all, you always put some of your solvent in first. So you fill the bulb at least partially because you need the solute to be in you need it to like mix around and you don't want it to like get all clumped together at the bottom. So it's easier if you actually add it to some solvent, okay? Now, part of the reason you only fill this halfway is because it gives you the ability to shake it a little bit better. Whereas when that neck starts to get filled with solvent, you don't have as much room for shaking. And so you can't shake as vigorously. Salt shakes pretty easily into your solvent, but other solutes aren't always very easy to dissolve and you really need to shake them to get it to happen. So my salt is in there, okay? And now what I have to do, and this is the tricky part, is you have to pour perfectly to that line, which again, yesterday's video, I was so proud of myself. I hit that line on the nose. It was beautiful. And of course, that video didn't turn out. So right now I'm guessing, you know, probably go over the line this time. All right, so I'm getting closer to the neck. You can see, oh, you can't see. I'm getting closer to the neck, so I'm slowing down, okay? You can see the line right there, right? I'm gonna try to go like drop by drop. This is where, you know, steady hands do help. I don't have to use a beaker. Like if I was somebody who had shakier hands, I might want to use a cylinder so that I can like really control the flow a little bit more. You know, right now I'm just showing off by using a beaker. I'll probably mess up because that's what happens when you let your ego get into it, right? Oh, I'm so close. I'm like literally drops away. And you could really cheat. Like if you're not cheating, it's not cheating. If you're like really drops away, you can like literally get a dropper. And oh yeah, see, I totally went over. I went over by a lot. Like, I mean, by a lot in terms of, so here's the thing, and I'm glad I did that. Like, so basically, you guys, I don't have a perfectly 0.15 molar solution because I went over, okay? Now, I probably only went over by a milliliter or two, but because my solute is dissolved, okay? And this is a good question, and they bring this up on the AP test. Because my solute is already dissolved in there, so I already have my 1.8 grams in here, and it was supposed to be 200 milliliters of water, but now I have a little bit extra water. So more solvent, more solution. How would that affect my molarity? Would my molarity be higher or lower than the 0.15 that I was expecting to make? If you answered lower, you'd be right, because keep in mind, like in that molarity equation, your numerator is staying the same. It's 0.030 moles. But let's say I have like 202 milliliters of solution now instead of 200. That means my denominator went up, okay, which is going to change my answer. Sig dig wise, is this really probably a big change? No. But if I was like really in the lab, I would probably dump this out and start over again, especially because salt's pretty cheap and easy to find. If it's an expensive solute, well, then you're going to have to take out the droppers and the graduated cylinders because you want to make it one time and do it successfully. Okay, now we're going to do a solution dilution, okay? So give me a second here. I'm erasing some of what I have from the slides that I made yesterday before I screen share with you. Okay. There, that should be good. All right, this part will go pretty quickly. Okay, so I'm going to screen share again. All right, and we're going to talk about the solution dilution. All right. Now, some of you might have noticed, I know like there were a couple of you when we did the molar volume lab, I ran out of the acid you needed and I needed to make it, okay? I didn't have 2 molar acid on hand. I had 1 molar, I had 3 molar, and I had 6 molar. And because I didn't feel like putting on gloves to pour the acid, I went with the 3 molar because it was more concentrated than I needed, but it wasn't as, corrosive as 6 molar. So if I spilled some on me, so what? I can rinse it off. So let's talk about how I did that, all right, for your lab. So if you want to make a more dilute solution, like if I said to you at home, like, here's a glass of orange juice, but it's too strong tasting to me. Can you dilute it? Like, what would you do? My guess is you'd add water, right? That's what chemists do, but they do it in a very specific way. They use this equation, M1V1 equals M2V2. This equation tells you how to take a more concentrated solution and turn it into a more dilute solution. Exactly, okay? Now, it doesn't matter if the concentrated solution is the one side or the dilute solution is the one side. That part of it doesn't matter. In fact, I'm going to do 2 examples with you and I'll purposely flip it. But let me tell you what we had to do for your lab, okay? So for your lab, you each needed 15 milliliters of 2 molar HCl, right? And I had to think about that you were each going to do 2 trials, okay? Which means realistically, each group needed 30. And I anticipated that when all was said and done, I'd probably have about 10 lab groups. Maybe not quite 10, but 10's a nice number because then it gets me 300 milliliters of solution. So if I end up having a little extra, good. That way, if like we end up needing more, I have it. As it was, I ended up having to make some more, okay? And so here's how this works. So basically, I figured out that I needed about 300 milliliters of 2 molar HCl. So using M1V1 equals M2V2, okay? What I did here was I knew I needed 300 milliliters of 2 molar HCl. Just so you know, in this equation, you can use milliliters or liters because you have volume on both sides, which means you're just getting this, as long as you're using the same unit for volume, it doesn't matter. In the other equation, you have to use liters because of the way the because molarity is defined as moles per liter, okay? All right, so I knew I was gonna use 3 molar HCl to make your solution, okay? So you know, 2 times 300 is 600. 600 divided by 3 is 200, right? So if I do that, you'll see my molarities cancel out. And what I found out was that I needed 200 milliliters of 3 molar HCl as my V2, okay? So what that meant was I needed to measure out 200 milliliters of my 3 molar HCl, okay? Now, let's look at this for a second. Is that it? No, because keep in mind, I needed 300 milliliters total of the weaker solution. So in order to make 300 milliliters of the weaker solution, remember, diluting a solution means adding water. So what this is telling me is that if I use this much of my concentrated acid and then add another 100 milliliters of H2O and mix them, that gives me my 300 milliliters of the 2 molar HCl. So when you're using the M1V1 equation, you're not just like doing the calculation and saying, like, the test will ask you sometimes, how do you make this solution? And you can't just do this math and leave it at that. Like, you need to say, you know, using a graduated cylinder, measure out 200 milliliters of 3 molar HCl, add 100 milliliters of distilled water, and shake or stir to mix, okay? All right, so I'm gonna do it now using the salt water solution we just made. We'll pretend my solution was perfect. I'm not remaking it for you. So we'll pretend that it's exactly 0.15 still. All right, so here we go. M1V1 equals M2V2. It says, what if I want to make 100 milliliters of a 0.010 molar NaCl solution using this one that I already have? Because sometimes, you guys, like, measuring out on the scale is kind of a pain. If I have one already and I can just pour into a graduated cylinder, sometimes that's easier, okay? Especially for solutes that don't dissolve very easily. Because if I already have it dissolved, then let's just use that if I can. Okay, so remember I said I was gonna flip it on you to show you it doesn't really matter. So my initial solution is 0.15 molar NaCl, right? And I wanna know how much of that I'm gonna need. So I'm gonna put V1 to make a 0.010 molar NaCl solution, and I want 100 milliliters of that, okay? So this one, I'm gonna need the calculator, all right? Oh, hold on. Wait a sec. Oh, I did this yesterday too. We're gonna try that again. Hold on. Okay, here we go. So let's do the math now. 0.010 times 100, right? Divided by 0.15. And when you do that, you get 6.7, okay, if you round for sig digs, okay? So you get V1 equals 6.7 milliliters. So take a minute, and that's of the 0.15 molar NaCl. So take a minute here, pause the video, and think to yourself, okay, so how would I make the solution I need to make? All right. Pause the video, work it through, and then you can come back and I will actually make it. So hopefully you paused, okay? So I'm gonna make this solution now. I have a 10 milliliter cylinder because that, you know, is pretty precise. I'm gonna pour our sodium chloride solution in here. You know, you really wanna look at the meniscus, right? Like right now, and I'm about 2, 4, 6, 8. I'm at about 6.5 milliliters. Again, this is like a question of drops, which is a little tricky. Yesterday I did better because it was the afternoon, so most of my coffee had worn off. Let's see. I can always pour it out if I go over. I totally went over. So I'm going to pour some out in the sink because I can. You have to consider what the substance is before you do that though. Okay, and now you guys, I'm like perfectly, I'm going to stop my share so that you can see that. Now I'm almost like perfectly at 6.7 because my meniscus is right below 6.8, but not quite on 6.6. Okay. So I have the amount of the concentrated solution I need. What else do I need? Okay. Well, I need 94.3 or 93.3, right? Yeah, 93.3 milliliters of water, which I'm going to pour some more water into here. So again, using a different graduated cylinder, you're going to measure the 93.3 milliliters of water. Okay. Sometimes it helps to like put like a piece of paper or something behind your cylinder to see the numbers better or to find like good lighting. Okay, I should probably do this so you can see. So I'm at about 90 right now. 4. Okay, there. I'm like right above the 93 mark. So that's pretty good. And then I'm going to use what's called an Erlenmeyer flask to make my solution. I'm going to pour my water in. You always want to be careful not to spill. And then I'm going to pour this in. And the reason I used a flask and not a beaker is because it's really easy to stir. And you do want to stir. And sometimes like I didn't grab one, but you can put a stopper in here so that you can like really shake it. But you don't want all the sodium chloride you added to just be like right at the top where you poured it. So make the effort to actually mix it so that your solution has a uniform concentration throughout. And that, my friends, is how you make solutions.